Greetings. Today we are going to talk about enthalpy of a system. Enthalpy of a system. So, when we carry out a process in a closed tube, so basically when we say closed tube or closed cylinder, then we're basically saying that the volume is constant. So when you carry out this, the heat content of a system is the same as the internal energy. Okay, so the heat content of this system, then we are saying, is the same as internal energy, which is denoted as E. And so when we look at work done in terms of pressure volume, which is expansion, then we say no work is done. Okay. But in a constant pressure process, the system and in this case is a gas expands. It expands, and so pressure volume work is done. And so the total heat content of a system at constant pressure, okay, the total heat content of a system at constant pressure, so pressure is constant, is equivalent to the internal energy plus the pressure volume work. Okay, and this is what we are calling enthalpy. This is what we are calling enthalpy of a system, and it is represented by H. And so we can define enthalpy as being equal to E plus PV. So let's look at enthalpy as a state function. So this is our equation 1. So in equation 1 above, the E, P, and V are all state function. And I believe we know what a state function is. If you don't, can you read it and familiarize yourself with this term? So H depends on the values of E, P, and V, must then also be a state function because it depends on these factors, which are all state functions. Hence, its value is independent of the path by which the state of the system is changed. Independent of the path. It is independent of the path. Does not depend on the path by which the state of the system is changed. So how do we then determine change in enthalpy? So delta H can be the difference of enthalpy of a system in the final state. So we are basically saying we're moving from H1 to H2. And so delta H then becomes H2 minus H1. Okay, but we know that H is equal to E plus PV, and so H1 will be equal to E1 plus P1 V1. H2 will be equal to E2 plus P2 V2. And so delta H will be equal to E2 plus P2 V2 minus E1 plus P1 V1. And so if you collect the like terms, then we'll have E2 minus E1, then plus P2 V2 minus P1 V1. And this gives us delta E plus delta PV, change in PV. So if we say P, if P is constant, so this there will be no change, and then so what we are having is delta E plus P, which is constant, delta V, and this is what delta H will be equal to. And we know that P delta V is equivalent to the work that is done, and so delta H will be equal to delta E plus work done. Okay, from first law, recall that delta E is equal to Q minus W, where Q is the heat transfer. So if we look at this equation here, if we look at these equations of delta H, where we have delta H is equal to E plus that, and this also being equal to delta E, then we can say that delta H is equal to Q, okay? Delta H is equal to Q when change occurs at constant pressure. Occurs at constant pressure. Okay. And this relationship is usually written as delta H is equal to Q subscript P, which means constant pressure. So delta H can be measured by measuring the heat of a process occurring at constant pressure. So what's the relationship between delta H and delta E? What is the relationship? So if you look at calorific values of many gaseous fuels are determined in constant volume calorimeters. So these values are given as Q equals to delta E. This is at constant volume. So when any fuel is burnt in the open atmosphere, that basically talks of infinite volume. Additional energy of expansion, positive or negative, against the atmosphere is also involved. And so the value of Q thus usually realized may be different from the equation. So the value of Q, which is delta H, is actually realized. This differs slightly from the equation delta H is equal to delta E plus PdV. So if gases are involved in a reaction, they account for most of the volume of the change, as the volumes of solids and liquids are negligibly small in comparison. So if you had a container and you have a gas, you have a solid, you have a liquid, then what we are saying is that the volume of this will be basically be determined by the volume of the gas. The volume of the solid and the liquid are negligible because this occupies space. So the bigger the space, the volume that is basically in that container becomes the volume of the gas. And so suppose we have N1 moles of gases before reactions and N2 after reaction, and we assume ideal gas behavior, we then have P V2 to be equal to N2 RT, PV1 to be equal to N1 RT, and so P delta V is PV2 minus V1 to be equal to N2 minus N1 RT. And so we have P delta V to be equal to delta N RT. And so if we substitute this in our equation for delta H is equal to delta E plus PdV, then we have delta H equal to delta E plus delta N RT. So this becomes our relationship between delta E and delta H. And so you can be given equations, some questions that you can then use to derive or to test the relationship of these two. Okay. An example is you have this equation, gas going to gas plus F2 gas, and you're given the delta E value to be equal to minus 14.2 kilocalories per mole at 25 degrees Celsius, and you're told to calculate delta H. So we know that delta H is equal to delta E plus delta N RT. The change in number of moles is, this is 1 mole, this is 1 mole, this is 1 mole. So there are 2 moles here, there's 1 mole here. And so delta N will be equal to N2 minus N1. What is N2? N2 will be 1 plus 1, which is equal to 2. N1 is equal to 1. And so N2 minus N1 is equal to 2 minus 1, and that is equal to 1. We know that delta H is equal to delta E delta H is equal to delta E plus 1, which is N, times 1.987, that is our R value, times 298 dividing by 1,000 so that we get our answers in kilocalories. So this gives us minus 14.2 plus 0.592, and that is negative 13.6 kilocalories per mole. So that is how we can relate delta H and delta E. Let us look at molar heat capacities. Molar heat capacities. So by heat capacity of a system, we mean the capacity to absorb and store heat. Okay? The capacity to absorb and store heat. So as the system absorbs heat, it goes into kinetic motion of the atoms and molecules contained in the system. As they absorb that heat, we see that the kinetic energy of the system is increased as the temperature of the system is raised. So if Q calories is the heat absorbed by a body of mass m, and the temperature rises from T1 to T2, the heat capacity, which is C, is given by C is equal to Q divided by M into T2 minus T1. And so the heat capacity of a system is the heat absorbed by a unit mass in raising the temperature by 1 degree. 1 degree, which is Kelvin or degrees Celsius, at a specified temperature. So when mass considered is 1 mole, when we can consider a mass of 1 mole, this expression can then be written as C to be equal to Q into T2 minus T1, which is basically Q divided by delta T. And this is capital C, which is the molar heat capacity. Molar heat capacity. And by definition, we are saying that molar heat capacity of a system is defined as the amount of heat required to raise the temperature of 1 mole of a substance or system by 1 Kelvin. And so since the heat capacity varies with temperature, its true value will be given as C is equal to dQ over dt. Small changes in heat absorbed and then changes in T. So dQ is small quantity absorbed, heat absorbed by the system, producing a small temperature rise, which is dt. So this can then give us a new definition of the molar heat capacity as the ratio of the amount of heat absorbed to the rise in temperature. Okay, so we can get the molar heat capacities at constant volume. Molar heat capacities at constant volume. And so we recall that according to the first law of thermodynamics, dQ is equal to dE plus pdV. If we divide everything by dt, so that we have dq over dt to be equal to dE plus p dv over dt at constant volume, and that basically means dv is equal to 0. The dv is equal to 0. Then what we are having is dq over dt, which is cv, will be equal to dE over dt at constant volume. So this becomes 0, and so the whole of this is 0 and leaves it as the dt or dE over dt. And so the heat capacity at constant volume is defined as the rate of change of internal energy with temperature at constant volume. Okay, so we then come to the molar heat capacity at constant volume. At constant pressure, sorry. Molar heat capacity at constant pressure from the same expression of dE over dQ, dE over dt, sorry, being equal to dE plus pdV over dt, we can then say that C is equal to dE over dt, we are opening this up, plus pdV over dt. But we know that H is equal to E plus PV. We differentiate with respect to T at constant pressure. When we do that, then we get dH over dt constant pressure is equal to dE, which is this, over dt constant pressure, plus P is constant, so we can only differentiate the volume, dV over dt constant pressure. So if we compare this equation, with this one, let's say this is equation A, this is equation B. So if we compare equation A and B, then you'll see that C, P, which is dE over dt, will be equal to dH over dt constant pressure. Can you be able to see the link between these two equations? And so the heat capacity at constant pressure is defined as the rate of change of enthalpy with temperature at constant pressure. Rate of change of enthalpy with temperature at constant pressure. That is the definition of the heat capacity at constant pressure. Now let's look at the relationship between Cp and Cv. Cp, Cv. From these definitions, it is clear that two heat capacities, they are not the same. And Cp is greater than Cv by a factor which will be related to the work done. So at a constant pressure, part of the heat absorbed by the system is used up in increasing the internal energy, okay, of the system, and the other for doing work by the system. So while at constant volume, the whole of heat absorbed is utilized in increasing the temperature of the system because there's no work done by the system. No work is being done. And therefore, increase in temperature of the system will be lesser at constant volume, at constant pressure, than at constant volume. And that is why Cp is greater than Cv. So we know that Cp is equal to dH over dt, and Cv is equal to dE over dt. But by definition, for 1 mole, we have H is equal to E plus PV. For 1 mole, for an ideal gas, we'll have H to be equal to E plus RT, because PV is equal to nRT and will be equal to 1. We differentiate this with respect to temperature, and so we get the H dt to be equal to the E dt plus R. Okay, because that will be dt, which cancels out, and it gives us R. And so, in relation to Cp, remember Cp is dH over dt, so we have Cp is equal to dE over dt, which is Cv plus R. So this becomes the relationship between Cp and Cv. So you can easily say Cp minus Cv is equal to R. And so this is the relationship between Cp and Cv. The last part will be calculation of delta E and delta H. We know that Cv is equal to dE over dt, and so dE will be equal to Cv dt from this expression here. So what we are basically saying is delta E will be the same as E2 minus E1, which is equal to Cv into T2 minus T1. T2 minus T1. And for N, for a gas with N moles, we'll have delta E to be equal to E2 minus E1, which is equal to N Cv into T2 minus T1. We know that delta H is equal to change into E plus PV, and this will be equal to delta E plus delta PV. This will be equal to delta E plus, remember this is equal to RT. PV is equal to RT. So that will be delta R delta T, because R is a constant. And so this, from what we have shown here, delta E, so it will be CV into T2 minus T1 to be equal plus R into T2 minus T1, because we're looking at change in temperature. And so this gives us CV plus R into T2 minus T1. CV plus R is Cp, so we have this to be equal to Cp plus into T2 minus T1. And so for n moles of an ideal gas, delta H will be equal to n Cp into T2 minus T1. So this becomes the relationship that you're having, how we can calculate delta E and delta H.